This is Mr. Parseghian, and today we are going to be talking about significant figures. In chemistry, very often we make different types of measurements and we make calculations with those various measurements. It's important that we report those calculations to the correct degree of accuracy, and that's where the concept of significant figures come in. There are 5 rules that we're going to talk about for identifying significant figures, and then we'll do some examples. Following that, we'll also do some different types of examples of calculations that we would make and how we would report them with the correct number of significant figures. Rule 1, non-zero numbers are always significant. So very simply, if you take a measurement and there are no zeros in that measurement, every digit in that measurement is a significant figure. For example, the number 2.54 has all non-zero digits, thus it has 3 significant figures. So now we have to think about, well, what happens when we do have zeros in our measurements? Number 2, zeros between non-zero numbers are always significant, or I would even say that zeros between significant figures are significant. So I like to refer to this as the sandwich rule. And so if you look at this example, 10.04, 1 is a significant figure, 4 is a significant figure, and there are 2 zeros sandwiched in between. They are both significant figures. So this measurement has 4 significant figures. Number 3, all final zeros to the right of the decimal are significant. The only reason you would have a decimal number that ends in 0 is if you've actually measured out to that place value. For example, I could say 3.4 and mathematically it has the same value as saying 3.40. The only purpose for putting the 0 on the end of that measurement is if I've actually measured out to the hundredths place. That means I have 3 significant figures. I also could equivalently say 3.400, and if I stated 3.400, the only reason to do that is because I had measured out to the thousandths place, and that number would have 4 significant figures. So you can write as many zeros as you want at the end of a decimal number. They will all be significant. Number 4, counting numbers, conversion factors, and constants have an infinite number of significant figures. So in chemistry, we'll use lots of constants and conversion factors, things like the speed of light or the number of centimeters in a meter, and we don't really count those numbers in our significant figure calculations because they are conversion factors and constants. So if I said 1 kilometer equals 1,000 meters, we would consider both of those numbers or measurements to have infinite significant figures. And then number 5, zeros that are placeholders only are not significant. And so if you think back to our discussions on scientific notation, you could have a really large number with lots of zeros at the end that, if written in scientific notation, would be removed. Those would not be considered significant. Or you could have a very small number with zeros at the beginning of that number, and if written in scientific notation, those zeros would also be removed and would not be considered significant. So if you look at this example here, the 2 zeros at the beginning would go away if I wrote those numbers or this number in scientific notation. And so here we have only 2 significant figures. The zeros at the beginning of that number are not considered significant. Let's take a look at some examples. All right, so the first number, 2.83, has all non-zero digits, so all of the digits in that measurement are significant. The second measurement, 3.6, also has all non-zero digits, and so both of those digits would be considered significant. Now, as we start to look at the rest of the examples, we see that there are zeros that are showing up in our measurements, and we have to decide what's going to happen here. Okay, so then the next example here, it says 14.0. That 0 is a trail 0 to the right of the decimal, and so that 0 must be considered a significant figure. If I did not want to show that level of accuracy, I could just as well write that number as 14 and still have mathematically the same value for that number. On our next example, the zeros at the beginning are placeholder zeros. They would not be considered significant figures. And so as a result, if we think about it, we can remove those zeros if this number is written in scientific notation, and so only the 3 and the 2 would be considered significant figures. On our next one, we have the same type of situation. We have zeros that are placeholders at the beginning of that measurement, and so we only have the 2 as a significant figure. The next one's an interesting situation. So on this one, we do have a placeholder 0 to the left of the decimal, but we also have a trail 0 to the right of the decimal. The placeholder is not significant. However, the 0 that follows the 3 is, and so that makes that 3 significant figures. In our next example here, we have 2 zeros that are sandwiched between the 1 and the 4. They would both be considered significant, and so here we have 4 significant figures. And on the last one in this column, the 2 zeros between the 3 and the 2 are sandwiched, so they're significant. And the 0 to the right of the 2 is a trail 0 to the right of the decimal, and so that is significant as well. We have 5 significant figures here. Now, if you look at the series on the right-hand side, it's kind of interesting because each one of those is the number 400 written out in a different way. So the purpose of writing 400 in those different ways is to express different numbers of significant figures. The first one, just 400, has 2 zeros that, if written in scientific notation, would go away. That is just 1 significant figure. On the second one, other than the power of 10, the only number we see there, the only digit we see there is the 4. That's 1 significant figure. On our third one, we have added a 0.0, and so that's a trail 0 to the right of the decimal. That's 2 significant figures. And on our last one, we have 2 trail zeros to the right of the decimal, and that makes that 3 significant figures. Okay, so now that we have established the way to identify significant figures, now we're going to talk about what happens when we calculate, when we add, subtract, multiply, or divide with significant figures. First, the multiplication and division rule. So if we multiply or divide, the way that we report the significant figures is to round our answer to the fewest number of significant figures in either or any of the measurements that are involved in that multiplication and division. The rule for addition and subtraction is different, and that goes by place value. And so if we're adding and subtracting numbers, the way that we would report to the correct number of significant figures is to round our answer to the fewest number of decimal places. Let's take a look at a couple examples. All right, first a multiplication example. Here we've taken 2 measurements, 12.50 and 2.05 centimeters, and we've multiplied them together. And the result of that is 25.625 centimeters squared. The question is, how many significant figures should we report our answer to? Well, if we look at our first measurement, 12.50, that has 4 significant figures. And in our second measurement, 2.05, that has 3 significant figures. So the least number of significant figures out of the 2 measurements is 3, and so as a result, we are going to round to 3 decimal places. So the first correction, we're going to round to 3 significant figures. So the first significant figure in 25.625 is the 2. The second significant figure is the 5. The third one is the 6. But before we decide how we report that calculation, we have to look at the number to the right of the 6. We know if that number is 0 to 4, we leave the 6 as is, but if that digit was a 5 up through a 9, we would round that 6 up. So in this case, we would report to 25.6 centimeters squared in terms of our correct number of significant figures. Here's a division example. So the measurement here is 45.673 grams divided by 6.1 centimeters cubed. This is very similar to a density type of calculation that we might have made earlier. And when we divide that out, wow, look at all the digits we come up with. And certainly, simply by dividing those numbers, our answer can't be more accurate than the measurements that we started with. And so now we have to apply our significant figures rules. So our first measurement, the mass, has 5 significant figures. Our second measurement, the volume, has 2 significant figures. And so we should round to 2 significant figures. So we know that we're going to keep the 7. And then after the decimal, we're going to keep the place value of the 4. But if we look to the right of the 4, there's an 8 there, which tells us that we have to round up to 7.5 grams per cubic centimeter. Now we're going to take a look at an addition example. So here we've got 2 numbers and we're adding them together. And when we add them together, we end up with 3.563 grams. And one thing that's important to recognize here is the addition rules are different than the multiplication and division rules. So the addition rules go by place value. So 1.51 goes out to the hundredths place. And then the measurement 2.053 grams goes out to the thousandths place. The least accurate place value is the hundredths place, and so we need to round to the hundredths place. If we look at our answer, there's a 6 in the hundredths place, and there is a 3 to the right of the 6, which tells us that we will not round up. Our answer is reported as 3.56 grams. Our final example today is a subtraction example. And so we have 2 measurements here, and we have subtracted those 2 measurements from each other. And we have a difference of 10.012 grams. So the subtraction rule is the same as the addition rule. Our first measurement has 5 significant figures, but it goes out to the thousandths place. Our second measurement has 2 significant figures, but it goes out to the tenths place. And so by subtraction rules, we are going to go by the least accurate place value, which is the tenths place. So in the tenths place, we have a 0 in our difference. And if we look to the right, there's a 1 to the right of that 0, which tells us that we will not round that up. And so as a result, we would report this answer as 10.0 grams.